So hello everybody. Myself Panthadeep Bhattacharjee and I am from School of Computer Engineering, KIT University, Bhubaneswar. So I'll be presenting the topic called density-based mining algorithms for dynamic data and incremental approach. So this is a part of the Ph.D. research symposium presentation of the ICDCIT 2022 conference. So here is the outline of my presentation. So I'll be starting with the research details, the goal of my research. This is followed by the motivation, what drives this research primarily, and this is followed by the applications and scope, so where the work can be used. And then we come to the working methodology of the research, the contributions preceded by the problem formulation course, and this is followed by the experimental results in brief. Finally, we conclude our work, and this is followed by the future research plans and publications. What's the broad area of this research? So it lies in the field of data mining, pattern recognition, and machine learning. The specific goals of this research are to develop incremental density-based mining algorithms for frequently changing data. And there are two mining tasks that have been handled specifically. They are clustering and outlier detection. So there are four contributions in total. Out of these four contributions, three of the algorithms are related to incremental clustering, and one algorithm is related to incremental outlier detection. And they all lie in the field of density-based uh, domain. So out of the four incremental algorithms, two algorithms are exact in nature, while two of them are approximate in nature. So what do we mean by exact incremental methods? So exact methods are those the output of which is exactly identical to the naive algorithm or the non-intelligent or non-incremental method. Whereas approximate incremental algorithms are those whose output is nearly similar to the naive algorithm. So naive algorithm cannot process data sets in their entirety with high degree of efficiency, and that's why we like produce the incremental extensions, and we deal with the dynamic or changing data. So here's the motivation behind our work. Usually we see that with naive algorithms or algorithms which only has the capacity to deal with static data, their runtime increases with the change in the data set. So as of now, as of this timestamp, so we have a certain number of data points. Uh, an increase may happen immediately, whatever the number of increases. There will be a change in the size of the data set. As a result, since we don't have a definite point till what we want to increase, of course we set the final limit when we run the experiments. But this leads to a gradual decrease in efficiency of the naive algorithm, and it also leads to higher consumption of resources as well. Moreover, there is the latency issue as well, where the processing of the data with frequent changes produces an output at a delayed time period. That means at the juncture where the output should have been produced, it gets usually delayed. And this can be a big problem when it comes to applying these sort of algorithms in some of the real-time methods. Moreover, one of the other disadvantages being since the amount of update is pretty small in nature, so the change in the output is also expected to be pretty small. So as a result, to touch all the data points in their entirety by the naive method is not going to be a wise option. So that's why we strive towards developing something smarter or intelligent, and hence the incremental extension come into the forefront. These are the applications of this work, possible applications. Traffic monitoring. So we can say that a GPS service provider gathers data from individual users about locations, and the density of the users at different places can change with the passage of time. So this is where the data is also changing. And if you have to find the traffic congestion patterns based on the change of the vehicular density or the density of people in that area, then such kind of algorithms can be helpful. Next, it also has its application in the medical research. So suppose individual patients are treated as data points, so they are associated with some number of symptoms. So as newer patients come for their treatment, now this data can be collected, and this collected data can be used for prediction of, say, epidemic, or prediction of a flu, or prediction of any diseases based on the data that has been recorded. Thirdly, the recommender systems. Say, for example, we have a platform like YouTube, where you see the suggestions that they are given. They are based on like the kind of clicks or the kind of like kind of videos that the user wants to see. So if you want a sports video or an academic video or an entertainment video, accordingly the suggestions will be provided. So the clicks are taken as the data points, so they can be treated as dynamic data points, and based on that the suggestions are also provided. The same goes for the e-commerce sites as well. When the orders are placed, and based on the orders that you have placed, the appropriate suggestions for buying the next item or similar item, similar to the kind of orders that you have placed, similar category of items, they can be suggested as well. So here's the problem formulation. So how we do it? So we assume that let t knife be the time required to find the output by a knife method, and the knife method is called as a knife, and tinc be the time required to find the output by an incremental method, and let it be called as ainc. So correspondingly, we have O knife is the output obtained by the knife method, and O and C is the output obtained by the incremental method. Let the memory notations be M knife and mem knife and mem inc produced by the corresponding algorithms. So we desire to establish the following objectives, which is that the time taken by the incremental method is less than that of the time that is taken by the knife method, and the outputs might be approximately equal or they might be exactly identical to the knife method. This is the output produced by the incremental method. We might have a memory trade-off. We might require some additional memory in doing so, but we have observed in certain experimental like basis on some data sets that we do not incur additional memory as well. But on some data sets, we have seen that there is the requirement of some extra memory as well, which can be a trade-off. So this is the scheme of the research. So suppose we have a data set called D, and some changes have been inflicted on the data set, and it changes to D prime. Now, if we apply the traditional mining algorithm, so which is like naive or non-intelligent rather, and it cannot process dynamic data sets intelligently, so it will produce a changed output. So let it be called as R prime. Now, the change between R and R prime can be very minimal. So as a result, because this is a non-intelligent method or a naive algorithm, it will eventually go on to process all the set of data points that it did for the base data set D, in order to produce that minimal change in output or reflect that minimal change in output rather. So this is not a wise idea, because as we go on inflicting more such changes, the size of the data set will keep on increasing, and as a result, every time to go back to the first point and try and process each and every data points that have been added till recently will lead to like heavy computation. The cost will be high, the consumption of resources will also be high, and as we mentioned in the disadvantages section, that there will be a latency issue as well, in the form of delayed production of output. So in order to come across this limitation or get rid of this problem, an incremental scheme can be proposed, which is that given a data set D, some additions or deletions can take place, and the updated data set gets produced. This updated data set in conjunction with the computational history. So what is computational history? This means that for every algorithm, for every naive algorithm, it has its components or building blocks. For example, say use of a matrix for replicating a graph, or for example, say maintaining a say simple data structure for recording the k nearest neighbors. So there can be different like components of a algorithm. So these components will go for a change. Once the changes are happening in the like number of data points, these components also have to be tracked basically, and together they form a part of the like incremental algorithm. But in incremental algorithm, we have to identify which components are more expensive. So we have to target those components individually and try and see if we can reduce the construction time of those components. And if you are successful in doing that, we'll retain the values of these components for the next iteration. That means when the next batch or next set of points are added or removed. So this actually goes on till the requisite number of data points are inserted or deleted. So we have taken care of both insertion as well as deletion. And the terminating condition is such that the requisite number of additions have been made or the requisite number of deletions have also been made. And in between, like every iteration, like an intermediate result is produced, which is collected. So this is just a record of what could be the result if this number of insertions or removals have happened. And since this entire scheme stops after the requisite number of additions or deletions have been made, whatever the final results that get produced, that is our final answer or final output. So it can be the clusters or it can be the outliers. Now, once the entire scheme is completed, this is now compared with the naive method. That means, had we not followed this scheme and we would have just gone for this naive method called A, what would have been our result? So, we have observed in two of our contributions that these results are exactly identical, both for the naive method as well as the incremental scheme. But for the remaining two algorithms, one from clustering and one from outlier detection, they are almost identical. But as expected, the efficiency of this incremental scheme is much, much better as compared to the naive method. So these are the contributions that I have made. So these are the name of the four algorithms. IMAS, incremental mass-based clustering. So what it does is that it's a point-based insertion clustering algorithm on a baseline called MBScan method. So MBScan is a very robust clustering method which relies on data-dependent distribution to find the proximity score between data points. So this is not a traditional distance-based clustering algorithm, in the sense that it finds its density by relying on the distribution of the data. But it doesn't have any incremental extension, so that's why we decided to extend it. But the extensions are only related to addition. So IMAS is in addition, incremental addition algorithm, and the additions are made on a single point basis. The second contribution is BISDB, which is batch incremental shared nearest neighbor density based clustering algorithm for addition. So this is different from the previous contribution in the sense that the data points are added in batches. The point-based extension has already been proposed priorly, so this is an improvement over that. And we have observed that with batch insertion, it has after a certain point of time, batch insertion performs better than both the naive method as well as the point-based insertion method. So here the results were exactly identical to the baseline, which is nothing but SN and DB scan. So SN and DB scan was the baseline. The extension is BISDBI. So the reason for exactness of results is that the graph that has been obtained or the shared nearest neighbor graph that was obtained that was actually identical for both the extension, incremental extension as well as the baseline. So once that is identical, the final clusters which are supposed to be obtained will also go on to become identical. So here, like some random parameters are actually involved. So as a result, like every time the change is reflected, it might not have exactly identical results, but it's almost near to the results produced by the MBS community. For the third contribution, we have VISDB del, which is nothing but an extension of SN and DB scan. But SN and DB scan was a knife method. This is a deletion incremental method. So like the way BIS to BID was an addition incremental method, this is a deletion incremental method. And it also takes care of removal of points in batches. So both for BIS to BID and BIS to BIDL, we achieved a higher degree of efficiency. And similar to BIS to BID, BIS to BIDL also has produced exact number of clusters as compared to SN and DB scan. KAGO and the last contribution, which is an outlier detection algorithm. So this extends a outlier detection algorithm called cannot. So cannot is a uh, naive method which cannot produce dynamic data sets and it relies on distance as well. But for KAGO, we have actually designed this method by finding the local densities of data points. So we have divided the entire set of data points in some grid cells, and for every grid cell, we find the local density with respect to that cell itself, local density of a certain point with respect to that cell itself. And in doing so, we find out uh, which are the most dense grids or denser grids. So the denser grids are accumulated to form the clusters, and the points which are left over, they are the outliers. So here we don't place stress on clustering, we focus on finding the outliers. And whatever individual outliers which are produced from respective grid cells, they eventually go on to become a part of the global outliers. We come to the experimental results. This is for IMUS. So IMUS here it's compared with the MDScan. So as you can see, the efficiency is much better as compared to the knife method. So there are eight data sets that we have used, out of which five of them are real world, three of them are synthetic. So due to constraint of time and space, we have included only few results to highlight the main results of this IMUS method. And these are the percentage of affected nodes, as you can see. So IMUS, like, it deals with you can say creating hierarchical models of subsets of the bigger data set, and every hierarchical model is represented by an I tree or an isolation tree, and the number of nodes which are involved in that isolation tree, they actually decide number of affected nodes. They actually decide that whether IMUS is going to be efficient over MBSCAN or not. And the lesser the percentage of affected nodes are there, more will be the efficiency, because only those affected nodes are actually touched upon. So you can see roughly around uh, 17 to 18% of nodes which are affected for data set called S1. So this is a synthetic data set. Similarly, for a data set called segment, which is a real world data set, you can see the percentage of affected nodes. So it doesn't go up. So x-axis actually denotes the insertion, pointwise insertion. So as we keep on adding more and more points, we don't observe a significant increase in the percentage of affected nodes. It rather remains on an expected lines. As a result, like IMUS ends up achieving a high degree of efficiency as compared to the MSK method. For BISDBED, which we had too many results, we are just highlighting the important ones. So we can see this is the curve of BISDBED, and it maintains its efficiency over both INSDB, which is point-based incremental method, as well as SNNDB, which is the knife method. So this is the SNNDB scan, the knife incremental method. And here we see an interesting cut point or an intersection point. So here the point-based method, it actually starts performing worse than the knife method after a certain number of insertions. So this doesn't happen in BISDB, as in the long run it is supposed to perform much better as compared to both the methods. This is one more demonstration of the results where BISDB ad is compared with the point-based method. So we can see that the speed up. So this is the speed up basically. For two data sets, MOPSI, which is 10,000 base points and 3,000 additional points. And BART's data set, so it has 80,000 base points and 20,000 additional points. So it has a total of 0.1 million number of data points. So you can see an increasing speed up. Yes, there was a slight dip here due to some computation reasons. So as you can see, the speed up gradually increases as we keep on increasing the number of points. Okay, so the number of points which are afflicted, rather, number of points of the base data set which are afflicted, as this keeps on increasing, the relative speed up also keeps on increasing. This is for BISTP del. Again, we measure the speed up of BISTP del over pointwise deletion. So it's an out and out batch deletion algorithm, but we also measured or we compared its efficiency with respect to pointwise deletion. So we removed one point at a time and compared the results. So finally, like, as the percentage of points of the base data set, like, it keeps on getting increased. So number of afflicted points of the base data set, as the percentage of it keeps on getting increased, the relative speed up of BISDB del over the pointwise method also keeps on getting increased. So we can say that this is more efficient than this, as more number of deletions take place. And finally, for the results of the KAGO algorithm. So again, KAGO appears to be more efficient than the Canard method. So this is for the NSL KDD3 dataset. So we primarily use NSL KDD3, NSL KDD4, and Yahoo search dataset with a KNN size of 15, and the base dataset size is that of 20,000. The total number of data points added are 5,000. So KAGO continues to maintain its efficiency even after all the requisite additions are made. and one of the reasons being the number of grids which are producing the outliers. So COG means candidate outlier grids. So out of all the grid cells into which the entire data space has been divided, only say this many number of grid cells were producing the outliers. The rest of them were not producing the outliers. So basically, we are targeting only this many number of grid cells. So that has played an instrumental role in saving the time for Kego as compared to Canon. These are the number of outlets. So this is for a sample data set NSL KDD3. So as we kept on adding the number of data points, you can see the number of outlets also kept on reducing. That's because a particular grid cell, say if it started with say around 140, 141 number of outlets, because of repeated insertion, that place has gradually gone on to become dense, and it is now overcrowded by the data points. So as a result, the number of outlets has kept on decreasing with increasing the number of data points. So Kego is like very much capable enough to find the total number of outlets after this many number of insertions have been made, and it does in a very less amount of time as compared to the cannot method. So I highlighted the efficiency here as this chart actually demonstrates. So, to conclude, we can say that real-time data analysis finds its importance in various day-to-day applications, and some applications we have already mentioned in course of our presentation. For example, for providing online recommendations to identifying threats in cybersecurity systems. The task of extracting information from dynamic data is not always easy because we cannot afford to deal with all the data points because the number of data points will go on increasing continuously. So we need to find some techniques where we only touch a fraction of data points and we end up finding exactly same result or nearly same result, yet maintaining a greater degree of efficiency. And these algorithms need to be curated in a manner such that high degree of efficiency is achieved. So there are no standard platforms as such, no standard template that given a naive algorithm, an incremental can be developed. We have to understand the individual components of the baseline or the state of the art method. And then you have to see which are the expensive components of the baseline method. Based on that, we target those components specifically and try and reduce its construction when a new data point gets inserted or an existing data point gets removed. So as a result, like the construction of the incremental method results into higher efficiency as compared to previous one. So these are the future research plans to extend IMAS and Kaggle. So IMAS is a point-based method, so is Kaggle. And clustering is an ill-posed problem, as we all know, because there are three postulates which doesn't get followed at the same time. So we tend to can say prove this further in the domain of density-based clustering algorithms. And these are the related publications that we have had. For IMAS, for BSDBX, this includes both the addition and deletion algorithms in batch mode. Then we had a survey of the density-based clustering algorithms. The CAGO also got published, and this was related to the initial part of BISDBX. So thank you. Thanks for attending the presentation.